So we move from graphing rationals to variation, which is a little bit of review and a little bit of new from Algebra 1. Let's start with direct variation. Okay, so if the statement says y varies directly as x, as you can read in the slide, it means that when x increases, y increases, or they have a constant ratio. So if k is the constant and I were to divide by x, the y over x is the same, always. There's your equation for direct variation, y equals kx. You'll notice also that that is the equation of a line in slope-intercept form with a y-intercept of 0. Inverse variation, I like thinking of inverse variation as when one increases, the other decreases, or their product remains constant. And lastly, joint variation is where you have a direct variation. Here's your y equals kx, but you're varying directly with a product of two terms, so y equals kxw. Now let's look at some application problems that describe each. I'm likely just going to set up most of these because solving is going to be pretty basic, but in a couple we'll solve. All right, so we know the period of a pendulum varies directly with the square root of the length of the pendulum. So if we set this up, period, we'll call P, varies directly, so that's K, and we need the square root of the length, like so. Now, in all of these problems, you either have a singular situation in which you're asked to solve for like a constant, or you have two situations, in which case you can solve this problem in kind of a unique way. So they tell you the length of the pendulum is 64 centimeters and the period is 1.6 seconds, and then they ask what's the period if the pendulum's a meter long. So this is a two scenario situation. So in theory, I have the first scenario and then I have a second scenario here. And you'll notice in both that if I solve for k, k is equal to P2 over root L2, and k is equal to P1 over root L1. You'll notice, since these two are both equal to each other, they form a proportion. And I typically like solving this way where we have two situations and I can then set two problems equal to each other, because then all I really have to do is find the missing variable instead of solving for k, because nowhere in here do they ask me to find the variation constant. So I'm going to go ahead and do that. We know that this is 64 centimeters. And then I have a square root of the time, which is 1.6 seconds. Now, the problem in this case is our other pendulum length is in meters. We have to use the same units in these in order to make our solution turn out correct. So 1 meter is 100 centimeters. And then I'm looking for the period. So this is some root x. So to solve this, pretty straightforward. We just take and do a cross product. So we know 64 root x is equal to 100 times the square root of 1.6. And then we divide by 64 and square both sides. What I'll do first, just for fun, is I'll take and reduce these guys. I know that 4 goes into both easily. This is 25 root 16 over 14, 15, 16, like so. That's square root of x, square both sides. 25 squared, 16, 16 squared. X is going to equal roughly 39.06. And that's going to be time seconds. The next example talks about a direct variation, and they ask us to find a variation constant. So this is a singular example problem or singular situation. I know that the volume varies directly with the cube of the diameter. So then I take 288 pi, set that equal to k times 12 cubed, and the answer will simply be without units because it's constant. Now we talk about an inverse variation. So it says y varies inversely with the square root of x. So I'll just say y root x is equal to k. Two situation problem. There's situation 1 and situation 2. So I take the y root 12, and that's equal to k, and the other k would equal the unknown y and the root 15. Isolate y. And you can pop that into your calculator and get a decimal rounded to 2 places. So now things get a little wordy. Just make sure you read carefully. Resistance varies inversely, so R varies inversely with the square of the current. And so we read through, and it appears to be a two-situation problem. So it says if a current of 8 amps or 0.8 amps requires a resistance of 50 ohms, and then they give us another current of 0.5, what resistance are we going to have? Again, simply take and divide 0.5 squared to both sides, and we get the resistance, which will be in ohms. So here's a problem with a little twist. It appears to be very similar to the last problem. However, it says this varies directly with the length and inversely with the square of the diameter. So there's two variations going in here. This is called a combined variation. In which case we need to write an equation where two variations occur at the same time. So if I want the resistance R to vary directly with the length, there is my direct variation. So to get the second relationship of an inverse relationship with the square of the diameter in, it's got to be inversely related with the resistance at the same time. So inverse would be a multiple with the resistance of the square of the diameter. So here, if you will, is the direct, and here is the inverse. And again, it appears to be a two-situation case. What I will do is say d squared r over L is equal to k, and then write that proportionally. So to solve this, I have 100 meters of wire. That's a length. Diameter is 6, and resistance is also 6. That's going to equal 80 meters, and I'm looking for the diameter. and I have 15 ohms. So in order to solve this, I'll multiply by the reciprocal of the second term and then square root. So I have 6 squared, 680 over 100 times 15, and all that will be square rooted to find my diameter, which should be in what, millimeters. And then we have our joint variation. Remember, that is a direct variation with the product, so the volume varies jointly with the height and the square of the radius. And again, they're looking for the constant, so this is a singular term. So I'll have V over H r squared is equal to K. Volume in this case should be 54. That would be cubic centimeters in theory. Right? And then I have a height of 8 centimeters and diameter of 4.5 centimeters quantity squared is equal to K. And then we just solve that problem from there. So those should be enough examples to get you through the assignment tonight, and we'll talk to you next time.